Okay, so I have two more examples, and what I'm going to be using are the techniques that we learned in the quadratics unit, just because they produce far faster graphing results than if we were to do everything by table of values. Just going to prep myself right here. Great. So, f of x, we have a function f of x, and that equals, I'm just going to do the positive, or I'm going to do the parent function without the absolute value, x squared minus x minus 2. So if I were to factor that, I would say f of x equals two numbers that multiply out to -2 and add up to -1, so x minus 2, x plus 1. So that's where we know the zeros of the function are. Now, there are a few things. The zeros, that's the same thing as x-intercepts, which is the exact same thing as critical points. Okay, these guys are all connected. I'm going to use them synonymously. So I know that I have x-intercepts. Oh, guess what I forgot to do? I bet you picked it out by scale. So I'm going to say this is 2, and this is 2, because each block is worth 1. Oh, and x and y. Oh, wait, little buddy. So I'm going to start graphing. So I have my one x-intercept at x equals +2, so right here. Another x-intercept at x equals -1, which is right here. Oh. Now, in order to find the vertex, I know that it's going to be in the line 0.5, okay? But what I'm going to have to use is I'm going to have to go back and remember the x-intercept is going to be x2 plus x1 divided by 2, which will give us that right there. So I'm going to say -1 plus 2 divided by 2 is, so this is for the x-coordinate, -1/2 plus 2, so that is 1/2, or 0.5. So what I'm going to do is I'm going to substitute 0.5 in here to get my true vertex. So y value vertex of vertex. And I would say y equals 0.5 squared minus 0.5 minus 2. Y equals 0.25 minus 0.5 minus 2. Y equals quarter minus 1/2 is -1/4, minus 2 is -2, and 1/4. So what I would actually like to do is I would like to say, well, actually, can we please change our scale a little bit? Yes, we can. So what I'm going to do is I'm going to say for every one of these, 1, 2, 3, 4, this is 1, 1, 2, 3, 4. This is going to be 2, 1, 2, 3, 4. This is going to be 1, 1, 2, 3, 4. So each one is actually going to be 1/4. Change my tune a little bit. We got to be flexible and gotta make work what works best. This is 1, and this is going to be 2. So if I were to plot my vertex, it would be at 1, comma, -1, 2 and 1/4. So I'm still going to keep my x-intercepts. They're still there. So my x-intercepts occur at +2, and they occur at -1. But my vertex here happens at 1/2, or 0.5, so which is right here, and negative 2 1/4 right there. So if I were to draw this parabola, it would look something like oh, and actually we can see from, if I were to put 0 in for my x, so I would find my y-intercept, it's going to be at negative 2, so we know that it actually does cross that 2. Like this. Just like that. So this right here is our parent function. So this is going to be y equals, or I can say f of x equals, y equals x squared minus x minus 2. But let's use what we know of absolute value functions to graph. So I know that here are my critical points, and anything that's above the x-axis is the same. So that will be like this. What we need to do now is we need to take anything that's below and reflect it upwards. So there are 2 points that we know. We know that our vertex is at half, comma, negative 2 1/4. So we're going to go half, comma, positive 2 1/4 right there. And I know that we have our y-intercept at 0, comma, negative 2. So it's going to go to 0, comma, positive 2. And in fact, since it's that's our line of symmetry actually right there, we can actually put that point right there. So when we would graph it, it would look like this. So this guy right here is going to be our f of x equals the absolute value of x squared minus x minus 2. So let's go and analyze it a little bit. So A, we figured out what the x and y intercepts are. So the y int occurs when y equals positive 2. We have the x intercepts when x equals negative 1 and positive 2. B, sketch it. Yep, did that. C, state the domain. So for a domain we can say x such that x is an element of the reals. You know how I switch it up sometimes with this? Sometimes I just say xer or x such that xer. It's whatever you want. Or we can simply say from negative infinity to positive infinity if you like interval notation. For range, I'm going to say y such that y is greater than or equal to 0. Y is an element of the reals. Or we can simply box it at 0, comma, positive infinity, just like that. As long as you don't do 1 in interval notation and then 1 in set notation, as long as you're consistent with your notation, that's all I care about. And D, piecewise functions. So for this, I went over, so y equals x squared minus x minus 2 for x less than negative 1 and x is greater than positive 2. And then the new part, the part that becomes the reflection, so y equals negative, the original, negative x squared minus x minus 2 for x is between negative 1 less than or equal to x less than or equal to 2. And we're done! Like I said before, you can distribute this negative into, or you can just keep it like that. It's all good.